All right. So we got some announcements, got to see Marcia, and we're back into two-wire sensors. So this is the last of the two-wire sensors I'm going to talk about, and this is a rheostat. And this is a variable resistor, and it works a little differently than thermistor, where the thermistor actually changes the state of the resistance on temperature. This has a little arm that moves up and down. So we use these, most commonplace is we use it in for the fuel sending unit. We also use it to dim the light bulbs, so we can actually use it as a control, so we can do more things with the thermostat. But what we're doing is we're making an electrical connection between here and the resistor. So if my connection is over here, that's going to be less resistance, more current flow. If my resistance is if my arm is over here, that would be more resistance, less current flow. So as we move in the fuel tank, as I'm closer over here, I'm full, more current flow. And as my needle moves down to this side, it would be empty, less current flow. So in order for this to work, I have to have a rheostat, which is the resistor here, a variable resistor. Inside the fuel gauge, I have a fixed resistor. Now, the fixed resistor in the old school fuel gauges, and this is true for temperature gauges, oil pressure gauges, any of those, the more current flow, the more heat is generated inside the gauge, and the resistor actually bends, and that's what physically moves the needle. So the more current flow, the more heat, the more full or the higher we are, the higher the temperature, the higher the oil pressure. Less current flow, we're down here. On newer cars, we still use this rheostat technology, but now we're going into a module with a fixed resistor, very similar to how we wired our NTC, and the computer's just monitoring the voltage on the wire between the two resistors to figure out, are we empty or full? So electrically very, very similar to our NTC thermistor that we talked about from a diagnostic standpoint. So if I disconnected my two wires to my fuel sending unit and connected this wire to ground, what do you think my gauge should read?
I'm sorry, what was the question again, Mr. Brian? I'm sorry.
If I disconnect my ground wire and my sensor wire for the rheostat and connect them together, what should my gauge read?
0.
Empty.
No, remember, the more current flow, the more the needle's going to deflect and the higher it reads. So if I short those two together, do I have a lot of current flow or little current flow?
A lot of current.
A lot.
Because there's no resistor there. Exactly. So when I connect those together, I'm going to see full. Or if it's a temp gauge, I'd see high, right? So now if I unplug them and I disconnect them, what should the gauge read?
Empty, 0.
Empty, 0, exactly. So here we have a dash, an instrument cluster, wiring coming from in front of you, all the way to behind you, all the way to the gas tank. And yet to test it, what we do is we unplug it, does it read empty? We connect these two wires together, does it read full? If it does, it proves all the wiring's good and the gauge is good. I need a sending unit. So you see how our understanding of the system, I'm not worried about the resistance at any given point here, although there's probably specifications. I'm just going to test, can we see empty? Can we see full? If we can do that and it's not working right, it's a problem with the send unit or the rheostat. So isn't it kind of interesting how we're really diagnosing this very similar to how we did our engine coolant temperature sensor yesterday, right? We'd unplug it. What does it read? We'd run a jumper. What does it read, right? Open, shorted. Can I see high? Can I see low? If I can see those, that means all the logic, all the rest of the components work. The part that I just replaced, that little sender, it's bad. And that's a lot quicker than guessing I have a sensor or spending a whole bunch of time, gee, I need a pot, I need to boil it, or I need to do this. And is this in spec or not in spec? Let's just make it easy.
Mr. Brian, good morning.
Yeah.
This is very interesting. Is this gonna improve later on? I was just wondering if there's a way that um, this whatever device is going to let you know exactly how much gasoline you have left. So you're not like guessing, are you really empty? Because they say that if it shows empty, you still have what about 2 gallons left before you really run out.
Maybe, right? Okay.
Okay.
Great question. Okay, so the old days, and not even that old, my 73 Delta 88, my first real car I had, when it got to half a tank, if I put my foot to the floor, the gauge would read empty because all the gas would go one way. And if I was coming to a stop, all the gas would go the other way and the needle would read full because there was no baffling inside the tank. So now, and the other thing is the send units used to swing front to back. So now a lot of the send units swing left to right or side to side so that we don't move as much with the acceleration and deceleration, and we mount it more in the center of the tank. We also put some baffling in the tank many times or some buffer so that the fuel is not able to move back and forth so much. So we did that in ways of trying to make it more accurate. So yeah, some of the cars now give you that mileage to empty, right?
Yeah, distance to empty.
Distance to empty. And there's a lot of people that, gee, it said I was going to run out and it's still going. And there's people that get mad because it said I had another 2 miles. Because what they're doing with that is they're approximating the fuel efficiency of the vehicle based on fuel consumption, based on the type of driving you're doing. So it's a learning, it's a close. Gas gauges are much more accurate now than they used to be. That being said, you should never run your car less than a quarter of a tank of gas. So,
Yeah, I actually learned that recently.
Yeah, because that's when fuel pumps go bad. So I usually talk about that with fuel pumps and why we don't go below a quarter of a tank of gas, because your likelihood of buying a fuel pump during owning that car is much higher. And some fuel pumps are $1,000. So it's pretty cheap to go fill up at a quarter of a tank.
I
Yeah,
do a
so
half. As soon as I get to half, I'm topping it off.
Right, exactly.
Yes,
Yeah.
that's exactly what I was going to say.
yeah, we learned that from Mr. Robert Jackson's class. I mean, I learned that.
Oh,
But
okay.
we used to have I think it was the Odyssey that we had. We still have it. And it had a problem before that it's not really giving you the correct estimate of your gas. So, even if it says so you had so much distance to empty, it will start like 300, like a full tank. And then all of a sudden it will go down to almost zero or empty. So
Okay.
what's happening then? But it got fixed later on.
Right. So was the gas gauge also moving that way?
No, it
No,
wasn't.
so it was just the trip computer.
Oh, okay.
Yeah.
So it's just a computer.
Just a little trip computer. So
The
I
other-
do have,
The other thing that it could be, because that's what happened to my van when I put it like like facing down on a hill, it will mark that it's like full. And when I put it like the opposite, with the front upside, it will mark that it's empty. So I think that will have something to do with it
right.
too.
Yeah. So, I mean, level, if you're not level, it's going to affect it, because it's pretty a simple little thing. So here's an actual rheostat we took out of a car. And you can see here where it has a little wiper arm, and it just makes the electrical connection between these two wires. And depending on where it's making the connection, the closer up here it's full, and then down here would be empty. So it just with how they wire it in based on where that arm is swinging, it's just making electrical contact. So consequently, these also wear out. Some of the new ones no longer have a physical contact, so they're technically not a rheostat. They're actually sending a signal through the plastic. Same theory, operates the same way, tested the same way, but the actual science of how they build it's a little different. But we've done this for ever. I can go to a 1950s car, and this is the technology we used. So this just hasn't changed.
Given the new ones, as you explained, don't have any physical contact, would you say that they're more durable? They last longer?
Yeah, and they should be, unless they're made by Nissan and they put them in a Frontier, because those were going bad left and right. But I think that was a manufacturing issue more than anything. But yeah, they should, because they don't have that physical contact. Because if I rub something back and forth, after a while, it's going to wear or wear through. One reason why we've moved away from that physical contact so much is the alcohol that we put in the gasoline. So with the alcohol, we have more corrosion issues, and we had more issues with this.
Mr. Brian,
Like
in order
a
to get
brushless
these-
motor is more efficient than, or more reliable and less parts to.
Yeah, a brushless motor is more reliable, but not more efficient.
Mr. Brian, in order to get to these, we generally have to drop the tank in order to pull these out. Is there an easier way? Because that's a pain in,
No, some cars have an access under the back seat or through the trunk floorboard, but many of them you have to, just like you said, drop the tank. And that's why getting to the wiring is key, because I can get to the wiring many times without dropping the tank. Either get my hand up there and disconnect it, or get to the wires where it's accessible. And I can run a jumper between those two and see if the gauge reads full now. Because usually people come in and they don't complain the gauge is full all the time. They complain it's empty all the time. Because that's normally how they fail, not always. But I can test it electrically by seeing, does it see full and empty before I ever take the tank out.
So if I can figure out where the wires are running through the chassis, then I can pierce them someplace in there and jump them together to test as well, right?
Right. And see, if you look at your wiring schematic, like on your Camaro, you're going to see a connector back there somewhere by the tank, probably inside the car where it goes down to the tank, where you have a bunch of wires. So you can unplug that connector and do your testing and jumpers there to say, hey, is everything good between the gauge and that connector, which means my problems between the connector and inside the tank, now it justifies taking the tank out.
Thank you.
And that's exactly what we do in the shop. I'm not going to take something out to see if it's the problem. I'm going to try to get to a test point and then prove everything else works. Then I can go back to the customer and go, hey, we tested it. You need a send unit. We need to pull the tank out. Then we're going to double check all the connections and everything when we have the tank out, because it's always possible a little wire could have broken or something on top of the tank you can't get to. But a shop isn't going to pull everything apart to test it. They're going to exclude everything, and then that justifies the labor to go in and actually take that part out, most likely replace it based on odds, but let the customer, hey, we're going to pull this apart, confirm that this part's bad, put a new one in. Here's the total price, parts and labor, based on what we think we're going to find.
Mr. Brian, I don't know if this is a fuel level sensor problem, but when I fill the tank, the nozzle, the trigger on the nozzle would pop up, and then I go back to look at the indicator and the fuel tank is not filled.
Right.
But the trigger has popped back up.
Yeah, that's most likely a vapor recovery issue. And we'll get into that a little bit more when we get into fuel tanks and talk about fueling, and I'll talk about what causes that to happen.
Okay, thank you.
I got some pictures to kind of help explain it.
Okay, Brian,
Yes.
maybe it's gonna be a dumb question, but it's just like something that I just been asking myself for a while. Like in these fuel tanks, any motor, as soon as you turn it on, it creates a spark, right? So
Right.
in the fuel tank, when it's like pretty much almost empty, you have those vapors there. That spark, can it ignite with that spark? Or I'm pretty sure that won't be the case because you have happened already. But I want to know, just like maybe because there's not enough oxygen in the tank to create, or what the deal is there.
Yeah, a great question. It's something that we thought about when they first started putting fuel pumps into tanks. So it's not a new thought. And it's certainly something we've been, thought about a lot, especially as technicians. The brushes are inside the pump, so they're always covered in fuel until you're out of fuel. And even when you're out of fuel, because of its design, the mixture is not where it's able to hit that magic mixture where you can have an explosion or a problem. And the brushes are also very small, not that it takes much of a spark, but they are immersed in liquid by design. And you never bench test an electric fuel pump, because certainly on the bench they warn that it could explode in your hand if you hooked it up to a battery and let it sit there run. On the car, that doesn't happen. What I do see is when people run out of gas, many times they burn the fuel pump up, or they damage it where it doesn't work anymore. So I have a feeling that the motor in there and the brushes is not real robust when it comes to being run dry, and very sensitive to overheating. So there's probably some fail-safe stuff they put in there to keep that. But there is no history of fuel pump motors causing cars to catch on fire.
Yeah. Okay. No, thank you. It's good to know, because it's something that I've just been asking, for a while. How come it doesn't explode? I mean, I'm pretty sure it creates a little spark or something there, but. Yeah.
Right. And I think that's the difference between me being a mechanic and an engineer. I look at it going, this thing should explode, and it doesn't. They must have figured something out. And I get bit and piece answers because no one thinks that we can understand the whole answer because we're mechanics. And yet, looking at it anecdotally, it's like they got it. It works, And some of the new motors are brushless. So we have moved to brushless fuel pump motors. I mentioned that a brushless motor is less efficient than a brush type motor, and that has to do with the phasing of the power. An inductive motor has some slip where the phase cycle can be greater than the actual rotor cycle, where a brush motor is going to be 1-to-1, so there's no slip there. The flip side of that is on a brush motor you have drag, where an inductive motor you don't have drag. So depending on what you're doing with it, there's different reasons. And we see that on hybrid engines, because all the hybrid motor generators are inductive motors. They're not permanent, they're not permanent magnet motors. So there is some phase slippage there. That's not true. They're not all inductive motors. So none of them have brushes, but some are permanent magnet. I apologize. So you have some motors, the phases match up, no slippage. Other ones, so you don't necessarily have slippage with induction. It depends on, induction is slippage, but brushless is not. I apologize.
So the fuel acts as like a lubricant and like a heat displacement for the fuel sanding unit?
For the fuel pump, yes.
Yeah, and
it is the lubricant for a fuel pump, and that's one reason why they have a lot of issues with alcohol that I'll talk about when we get into fuels.
So we keep saying the fuel pump and fuel level sensor as if it's integrated into one unit, but is it always integrated into one unit? I seem to remember fuel pump sitting outside the tanks at one point.
Right. If I go all the way back, machine, we had a mechanical fuel pump on an engine and a separate sender in the fuel tank.
That's me
Then
way back.
We went to electric fuel pumps on the frame rail and a sender in the fuel tank. Then we went to putting both senders and fuel pumps in the fuel tank. Most manufacturers put that in one assembly for ease of manufacture, but we see on vehicles that use what's called a saddle tank. That's where you have a drive shaft and the fuel tank comes down on both sides of the drive shaft and up and over like saddlebags on a horse. They'll have two sending units and a fuel pump, and it may be three separate or two separate things that go into those tanks. So most manufacturers do it as a modular assembly where the send unit, including this one here, actually clips on the side of the housing that the fuel pump sits in. but they don't have to do that. And there are manufacturers that don't, but it's two separate circuits. One is a pump circuit. One is a sending unit circuit. So there's 4 wires. Normally you'll see on those 4 wires, there'll be different sizes. I know GM does this. A lot of other manufacturers do. You have 2 big wires. Those are the pump. You'll have 2 small wires. Those are for the sensor because, again, the sensor is doing thinking. Little wires do thinking. Big wires do work. So obviously the pump's going to flow a lot more current than the send unit is. I need bigger highways. I need bigger wires. So that's another way when you're there looking at that and you see those 4 wires, you're wondering which is which. Look closely at the size. You'll normally see 2 are bigger than the other 2.
Thank you.
So do all rear wheel or 4-wheel drives have those saddlebag tanks?
No, a lot of 4-wheel drives like trucks have one tank just on one side of the drive shaft because they're long enough for that. We see the saddle tanks a lot on European vehicles, BMW, Mercedes, for example, and other vehicles that have that rear wheel drive, like my wife's Magnum, where it has that rear wheel drive low and the fuel tank's under the back seat or in the back seat bolster. So it is, saddle tanks are not uncommon, but the majority of manufacturers now make a front wheel drive vehicle. So there's no reason to have the saddle in the tank. They just put the tank back there and route the exhaust around it. Good questions.
How would you repair the sensor if it went bad?
I order a new one and put it in.
It's because I tried to find one and it's a lot harder to find on these older ones.
What do you call older?
1989 or 70s. Those ones are hard to get some parts for.
Yeah, some of those can be hard to get. I used to have a rebuilder. They've moved out of California now. That I used to have like a vintage 50s, 60s stuff. They'd rebuild them for me. They put a new circuit board in, and I mean, they did a great job. So there's still restoration shops to do that. Most of the stuff is still available. I can't remember the last time I had to have one built that I couldn't get one. They are, there are a lot of different ones out there, factory and aftermarket. I mean, there's not, like I said, I can't remember the last time.
Would you suggest putting a newer pump in if you can't find one? Find a newer one and then take that one apart just to get one little part out of it?
Yeah, but what kind of car are you talking about?
Old Astro van.
Oh, a Chevy?
Yeah.
Oh, those are still available.
Some of them I discontinued the part that I was looking for.
Well, you might have been looking. You might have to buy the assembly, but they're still available.
Oh, all right.
So
then it's cheaper, huh?
Right, exactly. I mean, you might have to buy the fuel pump assembly to get the send unit because they might not sell the send unit separately anymore.
Yeah, I was looking for that little sensor, the one that you're showing right here, the fuel level sensor.
Yeah, I mean, they still we can still get them for those. So either they're available, but I know you can get the whole assemblies for those.
Yeah, usually if the ones go bad, would they make the fuel level not go up? The gauge too?
It happens. The pumps go bad a lot more than the send units do.
Oh, because the sending unit was not even getting a signal for the gauge level.
Well, if it's not getting a signal, that's not the send unit's fault. It's just a resistor. The signal comes from the gauge.
Oh, yeah, it's because the gauge wasn't even, it was reading before perfectly, and then it just stopped it working. And then the fuel pump was still working.
Okay, well, that doesn't mean it's the send unit. That's why we disconnect the wire, jumper them, does it read positive, disconnect them, does it read empty. So does it read full, does it read empty? That proves the gauge and everything else is working. If it doesn't do that, you have a gauge problem or something going on up front, not a send unit.
It's because the fuel pump burnt out on it too at the same time as the gauge went up and down.
You have the worst luck.
Yeah, usually. No, it's not my friends. They bring it to me bad. They drive it on empty usually. I think that's the problem. Driving it on empty. make it cause burnout?
Yeah, not having gas could cause the fuel pump to burn out. It won't affect the sensor. I can't remember the last time I had a car I don't think I've ever had a car have a fuel pump and a sensor go bad at the same time.
Yeah. You
So,
this one I just ran into, that's why. So I was
Yeah.
wondering. He he told the car to me in the middle of the night, that's why.
okay. All right, well, let's do some review questions. So all 2-wire sensors work by changing the resistance in the circuit they're installed in. Is that true or false?
True.
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 Right? So whether we're varying resistance or whether a switch going open and closed, we're changing the resistance in the circuit. So 3-wire sensors. So 3-wire sensors, I can have a camshaft sensor. It could also be a crankshaft. EGR position, throttle position, manifold absolute pressure, and mass airflow. And so these are the primary ones that we see on the car, primary types. And we only are really looking at 4 types of sensor here. Because the TPS and EGR actually operate the same way internally. And we're going to see there's a lot more other similarities as we go through them. So a potentiometer. So some of you may be familiar with this with a stereo. In the case of an automobile, we wire them differently. So we're not changing the output the same way you would on a stereo. So I want you to kind of unthink that and just go with how I explain this. Most common type of position sensor contains a mechanical arm that is attached to a moving component, throttle plate, accelerator pedal, airflow door, etc., which causes it to slide across a fixed resistor within the sensor. So what we have is I have a 5-volt reference, and it's not drawn exactly right. The resistor is before this 5-volt reference, but anyhow, because the resistor makes the 5-volt, basically a transformer. So I got 5 volts that comes through here, through this fixed resistor to ground. That's my circuit. Simple series circuit, 1 resistor. My sensor between A and B is going to use all 5 volts every time. Not going to change. If it's different, we have a problem. Then I have this C, which is my throttle position sensor signal. And think of my C as a digital multimeter. And all we're doing is we're touching different parts on this resistor and measuring the voltage. So if I'm closer to B, which is my ground, I'm going to be closer to 0 volts. If I'm closer to A, which is my 5 volts, I'll be closer to 5 volts. So, right, because if I move this arm up and down, I'm going to go from, say, a 0.5 volt up to 4.5 volts. And so now it's just a matter of how I install it. So if I install it in a throttle, for example, and say, hey, I want a 0.5 volt when my foot's off the gas and 4.5 volts when I put my foot to the floor. Then all I'm doing when we work the throttle and I'm pushing the gas pedal is we're moving this arm up and down. And we do that today on drive-by-wire with the accelerator pedal position sensors are this type of sensor. It's a potentiometer. And then we have other of these in the throttle so the computer knows it's working the motor and the throttle correctly so that it's getting the right amount of angle. So this is pretty simple. And that when we test this, we're looking for our return on, in this case, C, my throttle position sensor signal. But keep in mind the difference between A and B on this schematic should always be 5 volts. So if I think I'm out of calibration or I think I'm not working right, one of my first tests is, do I have 5 volts at the sensor? If I have 5 volts to the sensor, then I'm going to check and see, does the sensor put out the normal range it should when I move the device, in this case, a throttle, but it could be an EGR position sensor. It could be an air door or a blend door between hot and cold. There's a lot of different things we use potentiometers on. Suspension, do you want your suspension low, in the middle, or high? Right? That's a potentiometer, right? We're just moving an arm across a resistor, telling the computer that your car is low, it's in the medium position, oh, it's in the high position. And so we can calibrate that, and we program it in that you know, hey, 1 volt is this, and 3 volts is this, and 4.5 volts is this, and it tells the computer when it's going to adjust the suspension height. Hey, I want you to take it till these sensors all read 3 volts, and it's going to adjust them all to that 3 volts. Hey, there's your middle setting or your high setting, whatever they program it in. So these little potentiometers are used throughout the car. And what we're looking for is a signal return. So the signal return voltage, my throttle position sensor signal, is viewable on normally a scan tool that supports data, or I could back probe it and look at it on a meter, a DMM, or a lab scope and see what I have. I can also open it and close it to see, does it move nice and smoothly? That's where I'd want to use a graphic multimeter or a scope, because I can see that it makes contact the whole time and that it doesn't make contact, stop, and then make contact again. Or if I'm looking at a DMM, I might miss that. And so, again, pretty straightforward on this. The first thing I want to do is I better be using all of my 5 volts. If I don't have 5 volts between A and B, then I would need to do a voltage drop test between A and F14 and between B and B3, right? Because if I don't have 5 volts there, someone else stole our voltage. We know that from our basic electricity. This is a series circuit. If my one load in a series circuit doesn't get all the applied voltage, I have to have another load. AE, bad connection, high resistance. If I have high resistance on the ground side, it'll cause my signal return voltage or my throttle position sensor to be higher. If I have high resistance on my power side, on my what's called VREF, voltage reference side, then my signal return voltage would be lower. So that's generally what causes them to be out of calibration more than the sensor itself. In the early days, we could adjust these throttle position sensors. You can't do that anymore. We haven't done that in at least 20 years, if not 30. So a lot of these are fixed now. And here is a throttle position sensor right here, and is mounted on the throttle shaft of the either carburetor, if I go in the Wayback Machine, or in this case, a throttle body. And there's when we open that up, it allows air to enter the engine. So we're going to measure how much, as you put your foot on the gas, how much are you opening this butterfly door, and that sensor is telling the computer how far you're opening it. That way it can adjust for the correct amount of fuel that you need, so you can actually go fast and the car not stall. So this is primary input, not only for fuel delivery, but it also affects how your transmission shifts. It can affect, it may turn off air conditioning. There's several other things. It can actually keep the car from starting. So these do quite a bit of stuff. This is a primary, the throttle position sensor is a primary input. Now, if you notice next to it, I have a manifold absolute pressure sensor that I will talk about soon. But if you notice, there's a lot of similarities between these two. As a matter of fact, 2 of the 3 wires are the exact same. So the green and black.
Question, Mr. Brian. Just a step back. So the 5-volt reference happens because of the resistor, right?
Right. The 5-volt reference is actually generated by a transformer in the computer, just like a transformer you'd have like on a train set as a kid, or you know, electric car set as a kid or something like that. And so it's transforming it to 5 volts. And normally that 5-volt reference is shared with all the sensors that use VREF. So all your 3-wire sensors tend to share the voltage, the VREF, the 5 volts, and they all share the ground. So if I have multiple sensors that aren't working or are out of calibration, that's when I suspect that I have a voltage reference or ground problem. If I only have one sensor with a problem, I'm really looking at that sensor or that sensor line.
Excuse me, Mr. Brian.
Yeah.
We're saying that we have 5 volts traveling from the PCM on the gray wire into the TPS.
Yep.
But then it goes through a resistor.
Yep.
And shouldn't the fact that it goes through a resistor change that voltage level?
Right. And that's why on the other side of the resistor, circuit 452, the black wire has 0 volts. because the resistor is a load. I mean, that could be a motor, right? I mean, a load's a load. It could be a light bulb or a motor. In this case, it's just a resistor.
Which means that if we put our DMM on if we back probe the TPS at A and B, it should use all the voltage.
Correct. Because it's our single load in a series circuit. Ohm's law says it has to use all the voltage.
So that also means that if we probe at C and B, then it won't use all the voltage. And in the case that in the way back machine on a carburetor, if I go and manipulate the throttle to move the butterfly, I should see the voltage changing.
Absolutely.
Okay, thank you.
And that's exactly how we test them. We go from, in this case, A to B. Obviously, they're not all A to B, but A to B, I got 5 volts. And by 5 volts, that may be 4.98. It may be 5.04. It's 5 volts, okay? I mean, we're not, the transformers are just not precisely at 5.000 every time. So that's normal, not a problem. And then I'm going to look at C, which is my signal return wire, and I want to see a change as I manipulate the throttle with the key off slowly. And I actually have a video in a lab that's going to be turned on today that actually shows me back probing and testing these sensors with a scope. So you'll get to see that, and there's a lab sheet on it. So, and I was just pointing out, I have another 3-wire sensor here, my map sensor that we'll talk about shortly. But I did want to point out that the wires, the pink and the purple and white and the green and black at the 2 outsides are the same wire. One of those is my VREF and one of those is my ground because they're shared. The signal return wire is going to be unique to each sensor. So if I back probe, which was our C wire, and I slowly open the throttle and slowly close the throttle, it should look the same on both sides with no dropouts. And you can see we're in seconds here. So I'm at about 3/4 of a second up to 4 1/4 seconds. So what I took 3.5 seconds to open it up and close it. And when you test these, you actually want to test them moving slowly, because if I have a spot that's bad, if I go fast, I might skip over it and not catch it, but it might cause a drivability concern for the customer. Also, if you notice, my 5-volt sensor doesn't use all of its 5 volts. It goes from about 0.5 volt up to about 4.5 volts. And that is our 90-10 rule. Sensors use the 90-10 rule. And what that is that they don't normally use the lower 10% or the upper 10% of the voltage range. So this is a 0 to 5 volt sensor, but it's only using 4 of the volts. It's using from 0.5 volt to 4.5 volts. Computer engineers do that on purpose, because that way, if this sensor went to the computer at 0 volts or at 5 volts, that would tell the computer there's a problem, and therefore it would set a code. So it allows the computer to see the difference between normal operation and abnormal operation. Abnormal operation being out or breaking that 90-10 rule. So it shouldn't go more than 90% of the voltage. It shouldn't go less than 10% of the voltage. Now, are things out of adjustment sometimes, and I might get 460 millivolts on my throttle position sensor, and I'm below that 10% threshold? Yes, that happens. That could be an out of adjustment TPS, or it could be normal for the car. Don't dwell on that. The 90-10 rule is more of a concept. It's really to explain why we should never have 0. We should never have 5 volts on a 5-volt sensor. And that's true for our 2-wire sensor or our 3-wire sensor.
So is that a standard base right there for open and closed? So you should read near 0 volts for closed and then near 5 volts for fully open?
Yep. Yeah, in this case, a 0.5 volt to 4.5 volts is a good normal range. Some cars might only get to 4 volts at wide open throttle. And again, it kind of depends. what kind of car, how much throttle movement do they have, those kinds of things. Ford's specification for closed throttle is under a volt. So GM's at half a volt, which is what I think I'm on here. Ford just is about 0.8 of a volt. So different manufacturers have different specs, but they're always under a volt and over 4 volts. I mean, so that kind of gives you an idea of what you'd expect to see. And this right here is very normal. If it's less than this, I'd look up to see if that's okay for that manufacturer a lot of the time. If the throttle was adjusted too high, so for example, instead of going down to half a volt, I went to 1 volt. The computer might interpret that as you still have your foot on the gas. So that means it's not going to control idle speed. It won't do other things that are required when you're idling. If it can't see the top end of the scale, it doesn't think you ever put your foot to the floor. So it's not going to give it as much fuel as it should on a hard acceleration. It also might not downshift the transmission when you're trying to pass somebody. So this is a major input of driver intent. This is what the driver wants to do with the car. So the throttle position sensor is really an input of driver intent. What does the driver want to do? They want to drive lightly, they want to idle, or their foot's to the floor and they want to go fast now. So it's really an intent sensor. And so it tells that to the computer so that it can adjust accordingly. The other thing, and you heard me mention that this can prevent the vehicle from starting. Generally, it's 3.8 volts. If I have over 3.8 volts on the TPS while cranking the engine, most systems, not all, but most systems will disable fuel, meaning that the computer will not inject any fuel into the engine. And they call this clear flood mode. And this goes back to the days of carburetors, where if you flooded a car with a carburetor, you would hold your foot to the floor and crank it, and that would allow air to come in, but it wouldn't allow a venturi to be created, so you wouldn't pull fuel in, and allowed you to clear the flood out. When we first went to throttle body fuel injection, like we see here, a lot of customers, this was when fuel injection was new, although this is an older throttle body system, they would put the foot on the gas, or the car wouldn't start, it would flood out. And so they put this clear flood mode in for customers so they could clear that flooding out. And engineers realize there's a value to that. So that tends to stay in. Not every car has it, but certainly the majority of them do. And it's called clear flood mode. And normally it's anything over 3.8 volts cranking prevents the car from starting. So here's an example where I could have a car that, hey, the computer's not turning on the fuel injectors. So the first thing someone might go, well, I need a fuel pump because there's no fuel in the engine. Or I need injectors because they're not turning on. Or I need a computer because the computer's not turning on the injectors. In reality, the throttle position sensor might be bad, or there might be a wire that's melted or shorted, and I have over 3.8 volts to the computer, so it's not going to turn on the fuel to start the car.
So that's why that's one of the options on disabling the cranking, like when you do the starter draw test.
Yeah, it doesn't always work. And obviously if it starts, get your foot off the gas right away. There's other cars that won't start if the computer thinks it's 40 below zero. So interestingly enough, we think of older cars having these problems. I had a friend of mine with a 2008 Lexus ES. And his car wouldn't start, and it was because a rabbit chewed through the wires going to the coolant temp sensor. So the computer was saying it was 40 below. So even though the computer set a code and knew it was lying, the car wouldn't start.
So Brian,
Yeah.
on these kind of sensors, on the previous slide, you mentioned that you have the A, B, and C connector. Since A and C are positive and negative, I was wondering, because it happened a while back on a truck actually, those two were reversed. and the car was just running fine. I mean, you know, it started right up. It was actually a cam sensor on a 99 Chevy pickup, 4.3 liter, and you know, start right up. But as soon as you turn it on, it was giving you a hard fault for the cam sensor performance range. So I went on all data Mitchell, and they both had the same wiring diagram, and the wiring diagram was wrong. Those two were reversed. So I was wondering why. I mean, because on the previous slide, there is no like resistor on the sensor itself that the computer will know. I'm just trying to figure out how the computer knew that it was, you know, they would reverse.
Yeah, if you reverse the power and ground, then your sensor would read opposite of what it should.
Will it be like just like the DMM that it will say negative, you know, because you have them reversed?
Right. Yeah, your DMM could read negative if it was reversed. And again, wiring schematics are wrong all the time. That's why it's important to know what has to be and how things work. And if it doesn't look like someone has been there before you, that's probably how it left the factory. It's been working fine for the last 10 or 20 years. Odds are your information's wrong.
Yes, somebody fixed it before, but they were following Mitchell and all data wiring diagrams. Actually, I even called Mitchell, you know, to let him know about this because you know, maybe, you know, in the future for another technician they will have the same issue because they're trying to follow a diagram and, you know, wrong. So
yeah, it's hard to overcome bad information. So let's take a look at a malfunctioning TPS. So here we're doing the same test. And in this case, look what happens. We start to open up the throttle, and then the voltage drops, and then the voltage suddenly comes back up. And we see that while I'm opening the throttle and while I'm closing the throttle. So you think about it, where do you spend most of your time? A little bit off of idle, right? We don't spend our time with our gas for. We spend most of our time in that area right off idle. So this particular car was having if you accelerate it, the car would actually accelerate, they kind of cut back and they kind of kick in. It would kind of give you a little bit of a jerk. Well, that's because the computer would start adding fuel as we open the throttle. Then it would stop adding fuel. Then it would give it a huge squirt of fuel and continue and drive normally. So this is what could cause a tip-in, what's called a tip-in hesitation problem. So, you know, it really is important. That's why we graph stuff, because if I'm just looking at a digital meter and the numbers change, I'd probably miss this. And that's the advantage of looking at things over time. Remember, our voltage return signal that I'm looking at here, all it is like a voltmeter testing different points on the resistor to see how many volts are in that part of the resistor. No current's really flowing through here. We're a DMM. There's a huge resistor inside the computer, and we are just measuring. And all I'm doing is I'm back probing the sensor to see what it's measuring. So,
now these potentiometers, do they have a physical contact on the wiper like the rheostat?
Yes.
Or okay, so it's most likely it's worn out because, like you say, to spend that much time in that area and the physical contact is wearing right there.
Exactly. Yeah, these do have a physical contact. They still have a physical contact to this day, and they do wear out. And that's typically where they wear out when they do on a throttle position sensor.
Mr. Brian,
yeah,
a potentiometer and a rheostat both measure voltage based on a physical position.
Okay. Well, they both send a signal based on the physical position. They don't.
Then we use that voltage that's coming back off of in order to either make it some decision. A gauge goes up and down.
Right. Okay.
Or
yeah.
make some decision based on that voltage coming back. But they both seem to be doing the same thing. So why are we picking one or the other?
Okay. So here's the big difference. With a rheostat, the current flow of the circuit is going through the connection and through the rheostat. Also, with the rheostat, it's getting normally battery voltage, or it's not as sensitive to voltage. With a potentiometer, we have regulated voltage going to it. The other issue is see, in a rheostat, it's part of a series circuit. In a potentiometer, we have a series circuit where we come from the gray through the resistor to the black, but the signal is measured in parallel. The signal is not part of that series circuit. So we're not changing the current flow through the circuit on a potentiometer where we do in a rheostat. But you're right, both are measuring something that moves.
So
I was just trying
contradiction
to figure out
happens.
the advantage to doing it one way or the other, because
Yeah.
in both ways we're sending voltage down. Well, in the rheostat, we're sending it down the same wire that's moving, but in the potentiometer, there are two separate wires. One's for voltage and one's for measuring the movement. So I was wondering if there was an advantage to using one or the other while we're making this decision.
Yeah, the advantage is that something like a throttle position sensor or any sensor, potentiometer is going to be more accurate and it's going to last longer. So you think about it, my level sensor, how many times am I going to fill up my tank with gas? Compared to how many times am I going to push down on the gas pedal and open the throttle?
Well, so, but I can push back and say that changing the level sensor in the tank is much more difficult than changing the throttle position sensor, because there's just a lot more labor involved. So I would want both of them to last a long time, the life of the car.
Absolutely. And that rheostat technology tends to last the life of the vehicle in the fuel tank.
Yeah,
So-
that's from a consumer standpoint. If you're a manufacturer, you want it to fail so you can get some money. If you're a dealer or something like that, they want you coming back.
Right. Well, and you also are looking at what's the expected life of a car. I can tell you it's 100,000 miles. So is that rheostat going to last in the tank for 100,000 miles? Yeah. Is it cheaper than a potentiometer? Yeah. We're not upgrading it.
My answer, my selection is one for that question.
And number one is correct.
Not enough.
It is. And that's the easiest way to think of it. Think of your signal return as a voltmeter. It's not part of the circuit. It's measuring the circuit in parallel to the circuit, but it's not allowing current flow. But you are right, Rob. Both the potentiometer and the TPS are both measuring position, but we use potentiometers for all of our computer circuits for that, because they're accurate, very accurate. They can be calibrated. We feed a fixed voltage into them, and we're not flowing current through that contact. We're just measuring. And when you flow current through something like a rheostat, you get a certain amount of arcing each time you change position. I don't know if anyone's ever had dash lights on a car that you move the dimmer and you hit a spot where they kind of go out, then they come back, and you do this a couple times and then they work okay again on an older car. Anyone ever have that?
Yeah, we did.
So that is a rheostat. And the reason why you lose that contact is because of that arcing through the connection. And when you're doing this, you're cleaning that connection up again.
Yeah.
Well, we don't want that in a computer circuit. We want something that's very, very accurate. These are sealed. So these potentiometers are sealed. You can't get into them. And again, they're designed for the life of the vehicle. Do they last the life of the vehicle? No, thankfully not, because that way I have something to do. Do they last a long time? Absolutely. And again, think about how many times you're pushing down on the gas and letting it up on the gas, depending on how many tanks of gas you're replacing. So a much more repetitive motion, and the potentiometer is going to allow us to do that. And back to your comment about, you're right, I really don't want to take the tank out to get to things, but manufacturers don't seem terribly concerned with how hard it is for us to fix something when it breaks.
That's true, I think.
Yeah, they're concerned with how easy it is to put together on the assembly line, not how hard it is to take it apart and fix it.
But Mr. Brian, if I may say this,
Uh-huh.
I know I don't have to learn everything because I know I
Right.
won't. But that throttle term has come up a few times, and I thought it was like a gas pedal, so I'm completely wrong.
Well, you're not completely wrong, because the gas pedal is attached by a cable or linkage to the arm that's moving for the throttle position sensor.
Okay, so it's just a part, right? It's not
Yeah,
an actual gas pedal. Okay, I had to read up
exactly.
on the side. I was
No,
Googling.
and on your newer car, Dell, which doesn't have, it still has throttle position sensors on the throttle, but now we use that exact same sensor, actually two of them, and put them on your gas pedal. So now as you move your gas pedal up and down, it's called an accelerator pedal position sensor, APP. It's going to, as you move that up and down, it tells the computer where you want to be, and then it moves the throttle and measures with the TPS that it measured it to match what you want. Or sometimes it deliberately doesn't match what you want on drive-by-wire cars. Maybe your tires are starting to spin. So even though you want to go fast, we're going to let off the gas so the tires can get grip, things like that. And I have an article coming up when we get into fuel systems in a few weeks that deals with drive-by-wire. That's pretty good and kind of talks about the technology and talks about why we use it and the advantages it gives us. So that'll build on what we're talking today, Del.
So
Okay.
the throttle refers to both the gas input and the air intake, right?
Right. So the throttle is the throttle plate. And when I open that up, air comes in the engine. On a carburetor, gas would also come in the engine. On a fuel injected vehicle, only air is coming in the engine. It's the signal input from the TPS along with other inputs that go to the computer that make it decide when and how much gas to put in the engine.
I'm just curious as to how some of our classmates, like Mr. Rob, Mr. Christopher, and Albert, know so much. It's like they're way ahead of us.
I started with Frank Vasquez. So I did this. I've been at this for like, I want to say like a year now. And this will be my last portion. I actually did it. I did FOOS because Brian wasn't available at the time. So I kind of took it out of order, but this will be my last class to get the certificate if I pass.
Yeah. And I think a lot of it also is it just means they've made more mistakes and screwed more things up than you have. Because we learn by making mistakes. We learn by doing things. I don't care if it's in the car or in the kitchen, right? I mean, I look at the things that I've done, and every time I do them, I get slightly better at them, whether it's doing drywall repair or, putting in an outlet or working on a car or gardening or anything I do. We learn something each time we do it when we kind of look in and go, I should have done that a little different, or, I'd like to do this different, or you watch someone else. Ooh, I haven't tried doing that way. That looks easier, right? We're always learning.
That's
You're
true.
right, Mr. Brian.
Spend time under the shade tree.
Yeah.
You're right, Mr. Brian, because when I was growing up in the Philippines, my dad had to run a bunch of jeepney for transportation for way of living. I'm the one who putting the taking out the old shock absorber and putting the new one. I was 10 years old that time. I was crawling down the ground just to check the shock absorber of what the jeepney.
Yeah.
I learned by experience. It's also for the carburetor, the old school, the fuel system, carburetor. Yeah, it's hard for that to be flooded.
Right. And I'm sure it didn't work the first time. So you take it apart and try again until, this is better. And then you kind of learn from somebody and you try something else. It's how we learn everything. I love learning. I have enjoyed, I've had some great tradespeople here. And I've done, quite a fair amount of drywall for someone who didn't do it for a living. And watching some of the things and some of the technology advances and some of the drywall guys are doing, or some things have changed in framing. I was talking to the guy who did some framing and saw that, hey, you did this different. We're not doing this now. Nope, this is no longer code. Now we do it this way. So I was able to see some different ways they're doing it, some different tricks that'll make it better the next project I do. So I just love learning all kinds of stuff.
Yeah, when I was growing up, I learned it from vocational course. I enrolled in a vocational school which covers the auto and diesel mechanic. I
Oh.
learned a little bit. That's why I have some little experience of an engine and some gas and diesel engine.
Yeah, you know, again, it's just I'm watching them do concrete, and I learned I've done some concrete, no big projects, but I learned a bunch of tricks on finishing concrete. So I have to do a porch slab, and I'm going to do that myself. And I'm looking forward to doing it because I've learned some new tricks to get a better finish. So I love learning.
I don't know about carpentry or masonry. I like gardening.
Brian, in the fuel injection system, is flooding still a problem?
No, that's not to say that they never get flooded, but they normally get flooded due to a malfunction in the ignition system or a sensor. They won't flood under normal operation.
Let me say that I didn't mean to offend the people that I singled out. I admire you all. Thank you.
Oh,
You know, I'm actually I'm working as a mold mechanic, and you know, I took actually some classes in Spanish, but you know, right now just trying to get you know most of the certificates, you know, like from actually school, and the ASC will be the other, you know, the other ones that I want to get to. But definitely, there's like Mr. Ryan said, there's a lot to it. You know, once you actually get into books, you learn a lot. You know, why they do this, why they do that. And, you know, that's actually really interesting. You know, it keeps you going. In my case, yeah.
Yeah, and I don't think you offended anybody, Del. I think you really complimented some people because we have some people in this class that do have a lot of experience and really, you know, I can tell by their questions and their comments that they really know a lot. But yet you can see they're here because they want to learn more. They're trying to put the pieces together or to make things easier for them to do. So I mean, I think that's why we're all here, is to learn and share.
That's good.
So that was our TPS. So let's look at our EGR position sensor. So this is a sensor that instead of measuring something that swings, measures something that goes up and down. And so the computer must be able to verify the EGR is moving correctly when commanded by the PCM. So if the computer turns something on, it wants to make sure that it actually turned on or it actually moved. So as the diaphragm goes up and down the EGR, we're going to put a plunger on the top of it, and that plunger is going to go up and down. And we're going to have a resistor on that, and we're going to measure where that goes. Oops. There you go. So there's our EGR position sensor. This is an older Ford one. A lot of them are built in now, but it's a potentiometer. It works the exact same way as the TPS. Has a voltage reference, a ground, a signal return, works on 5 volts. It works exactly the same way. We're going to test it exactly the same way. The only difference here is we're measuring something that's moving up and down versus something that's rotating. We're still measuring change on something. We're just measuring that change. So it's the same thing. Now, some older vehicles pre-OBD2 will have three wires going to something on the throttle. Mercedes did this. The old Bosch L-Jet systems that were used by both Toyota and Nissan did this, as well as on the European stuff. What they did is they used 2 switches. So it's 3 wires. But what they did is they either used, Jaguar did this also, even into the 90s. So what they said is, you know what? Our management system doesn't need to know everything the driver does. I need to know when the driver's in idle, and I need to know when the driver slammed their foot to the floor. That's all we want to know. The rest of it we got. And so what they did, it was actually a pair of switches, and they wired them a couple different ways. But basically you had an idle switch and a wide open throttle switch. So if you're working on something pre-96, you may run into these. Everything 96 and newer is going to use our little throttle position sensor that we're looking at right here. So if you're working on something 96 and newer, great, you're working with a throttle position sensor. Same rules apply. They all work on 5 volts. They all work the same way. Boy, that gets pretty easy at that point, doesn't it? Because now it doesn't matter whether I'm working on a Mercedes or a Honda or a Chevy, because the circuit works exactly the same way. The throttle position sensor works exactly the same way. Now, the minimum and maximum voltages might be a little bit different, but they're still going to be in pretty close to the same range. And that's why we have specs. But if I'm working on something pre-96, be aware there are systems out there that use 2 switches in one housing with 3 wires instead of a throttle position sensor. So if you're testing it and it doesn't act like you think it should, or you see something weird, just take a look at that and do your research and see if this is potentially what you have. Because like I said, Mercedes did this. A lot of manufacturers did this. So the Mercedes CIS did this, which is Bosch K-Jet. So there is systems there. They really came from Bosch, but they were also used by a lot of Asian manufacturers. Not CIS, but the L-Jet was. So some of the electrical assemblies mounted on the throttle shaft are actually a pair of switches and not a 3-wire sensor. Is that true or false?
True.
That is true. You sound like you're the only one who's sure. No one else wants to speak up, but it is true.
It's true.
No, she just beat me to it.
Okay.
It's true.
You just explained it like 10 seconds ago.
Yeah, but you know what I found in person? When I do these in person and I have the little responders and everyone as they come in the room gets a clicker to put up their vote. It's amazing how few 100% I get. I'll go weeks without getting the class to vote 100% on something. Even though you said I just explained it.
See, I'm muted.
That's
So by the
cool,
time I
Brian.
unmute myself, somebody already answered. So
No problem. I just like to know I'm not alone.
you're not. We're with you.
So pressure sensors. So atmospheric pressure in this room and in the room you're at is 14.7 psi or 29.92 inches of mercury, depending on the weather. It moves slightly up and slightly low. You know, when they talk about the weather, a high pressure area or a low pressure area, we're moving up and down a little bit. Or 1 bar is another way of expressing that, is barometric pressure. And so it would be, so pressure sensors monitor the pressure differential between atmospheric pressure and the pressure within a component or system. Pressure sensors also monitor our barometric pressure, atmospheric pressure, or baro as it's abbreviated at, because if I go to Denver, my outside pressure is different, right? The air is thinner, right? It's easier to hit a home run. It's easier to kick a field goal. The air is thinner. It weighs less. Well, in the engine, we meter our fuel by weight. And we need to put in the correct weight of fuel to match the weight of the air. So it's critical that we know what the air pressure is, hence the baro. There's other pressure sensors. What about maybe I need to know the air pressure inside the intake manifold, or pressure inside air conditioning system or other things. So or inside my fuel system, we have fuel pressure sensors now, both for the rail and the supply. So like if I'm looking at a 2018 Ford Ranger with direct injection, it has 2 fuel pressure sensors, one on the rail for the high pressure and one on the supply line for the low pressure. So we're using more and more pressure sensors, not less. If I have a car with a turbocharger, I probably have a boost pressure sensor. I want to know how much pressure I'm boosting. So the internal technology of these is basically the same. And I could get into the internal technology, but the reality is I just don't care that much. I could make your heads explode. We could get into how a Wheatstone bridge works. We could spend a couple days on it and it wouldn't help you fix one car, and I would confuse everyone in the room. So that being said, it doesn't matter whether it's a Wheatstone bridge or pixie dust. We need to understand why we measure pressure, how that pressure measurement affects how the engine works, and how that sensor works once we leave the sensor and get to the computer. Because that's where we test. I'm not opening the sensor up to measure the pixie dust to make sure there's enough there. Just like I'm not going to open it up and test the Wheatstone bridge. I'm going to test it from that connector to the sensor between there and the computer. I'm going to look at the voltage coming from the sensor to see how does that affect how my computer operates. Does it really know it's at sea level, or does it think it's still in Denver? Those kinds of things. So pressure sensors are 3-wire sensors. The 3-wire sensor has a reference voltage wire, VREF, from the PCM, a ground, and a signal. Doesn't that sound like a TPS? Didn't a TPS have a VREF, a ground, and a signal return?
Yes.
Isn't that the exact same thing
Yes.
the TPS had? So common sensors that we use that today, I've got a few of them here. Manifold absolute pressure sensor, fuel tank pressure sensors where we check for evap. Like I said, evap goes with it. Barometric pressure sensor, delta pressure feedback sensor, fuel pressure sensor. And I need to add some more because we've added a bunch more in recent years. But here's my little map sensor. And my map sensor has a vacuum line that goes to the intake manifold that measures my manifold absolute pressure. So when we think about things, there's 2 kinds of pressure. There is gauge pressure. I look at a gauge and it reads pressure. And I have absolute pressure. So absolute pressure, my absolute pressure in this room is somewhere around 14.7 PSI. My gauge pressure in this room is 0. So if I look at a gauge, it's going to read above or below that 0 mark. So if I'm measuring vacuum, it's below. If I'm measuring pressure, it's above. So my manifold absolute pressure sensor is measuring pressure from absolute 0. So it's going to measure pressure in the intake manifold without the engine running. And then it's going to see that pressure drop once the engine starts. So this is an absolute pressure sensor. And this is one of the 2 types of load sensors we use on the car. So on a vehicle, if I want to manage an engine, I need to know how fast it's going. And I need to know what kind of load it has. So for example, my engine might be running at 3,000 RPM, but my foot's off the gas and I'm coasting to a stop. I don't need really very much or any fuel for that. On the other hand, I'm at 3,000 RPM and I'm accelerating going up a hill. I need a lot of fuel for that. So here my engine's going the exact same speed, but the load, the amount of work I need the engine to do is very, very different. So we have 2 types of load sensors. One is a map sensor. The other is a mass airflow sensor. So if a car uses a map sensor, it's called a speed density system. We're measuring the speed of the engine, density of the air. Or we use a mass airflow sensor type system where we're actually measuring the air going in the engine. So those are the 2 systems we use. And we'll look at more of those when we get into fuel control, but I wanted to introduce you to load sensors here while we're talking about sensors. And this is a 3-wire sensor. And if we look at the schematic here, they're not showing us the magic inside the map sensor. But what do I have here? I have a VREF, and it says, oh, it goes to TPS. So we're sharing the voltage reference with TPS. So I got 5 volts. And then we share it to the EGR we already talked about. And then on A is what? Ground. And B in the middle is my signal return. Doesn't this look exactly like a TPS in the wiring and how the wiring works with a power, a ground, and a signal return?
I think it does.
Yeah. Couldn't I test it the same way? Shouldn't I have somewhere between high voltage, again, following that 90-10 rule, and go look up maybe what the specification is for key on engine off versus 20 inches of vacuum, or there probably gives you some specs in there that you should have this many volts at key on engine off, you should have this many volts at idle, and so on.
Oh, these are all potentiometers as well.
It's not a potentiometer. I use the potentiometer because it's the easiest to explain how we change the signal return voltage. Inside here, many of these use what's called a Wheatstone bridge, but there's a couple other ways of doing it. It's a variable resistor that basically has a diaphragm that changes the resistance based on pressure to kind of oversimplify it. But that's what I was saying. It could be pixie dust. It doesn't matter because we're not opening it up. What I need to understand is based on the amount of pressure or vacuum, it changes the amount of voltage it sends on the signal return. Just like on my throttle, whether my throttle's closed or open, changes the amount of voltage on my signal return.
Just to be clear and not to open it up, but what we're really doing is replacing the resistor of a potentiometer with the vacuum sensing.
You got it. Yep.
Okay.
With,
Thank you.
with vacuum sensing pixie dust.
Perfect. That's what I'm writing down. Pixie dust.
Yeah, and people laugh at me because I'm a technical guy. I'd have to I'd have to look at the picture of the Wheatstone Bridge, but I could walk us through it. They're pretty confusing. I've seen people kill themselves because they think students need to know it. And it's like, you're never opening it up. You're never testing it. What difference does it make? And one of the things that's helped make me a better technician is understanding when certain things are just magic pixie dust. I can't open it up. I can't see it. I need to understand what it does. How it does it really isn't going to help me fix the car. In this case, I need to understand it reacts to absolute pressure. So I'm going to have specifications, just like we did in our temperature chart for key on engine off. I should have 4.5 volts or 3.8 volts or whatever the specification is. At idle, I should have a volt or 1.2 volts or 0.8 volts or whatever that manufacturer specification is. And that's how we test this. So if I don't have the correct voltage on B, what am I going to do? I'm going to jumper between A and C. Do I have 5 volts? If I do, and I don't have the correct result on B, key on engine off, I got a bad sensor. I mean, it's that straightforward. On the other hand, if I don't have 5 volts when I go between A and C at the map sensor, I need to go find who stole the voltage. I need to go find that bad connection. So we're going to diagnose this exactly the way we did a throttle position sensor, except for instead of moving a throttle back and forth, we're going to turn the key on and not have the engine running. Then we're going to start the engine and see what it does. And then usually there's a spec for somewhere around 2,000, 2,500 RPM. We rev the engine up and see what the vacuum is. I mean, so it's pretty, it's very similar to moving a throttle, except for here we're doing the other. So power, ground, signal return. So my next question is, and the key one is, both the TPS and map sensor circuits work the same way electrically from outside of the sensor to the PCM. Is that true or false?
True.
True. And let me tell you, that is the home run thing from today. Is I want you to understand that a 3-wire sensor, once we get out of whatever magic is happening in the sensor, is a 3-wire sensor. We got a power, a ground, a signal return. Now the signal may vary by the type of sensor. Its specs are going to vary by the type of sensor and manufacturer. But when I look at it electrically, power, ground, signal return. It doesn't matter if it's a 3-wire sensor that's mounted to a control arm underneath a vehicle. I don't care if it's a 3-wire sensor mounted to a blend door in a heating and ventilation system, or if it's a 3-wire sensor mounted to the side of the throttle. Power, ground, signal return.
Sir Brian.
One question, sir. Mr.
Yes.
Brian. Regarding the barometer pressure 14.7 PSI, I have question, or maybe away from this topic. For the lambda value of the Strochi also has a value 14.7 pound.
It's one of those magic numbers, isn't it?
Magic or coincidence, I can say.
I don't know. I'm not an engineer, but you know how there's certain things in science that keep popping up, and that seems to be one of them for us in automotive.
No, both related to the pressure also.
Yeah. No, it's one of those magic things.
Okay, thank you.
Mr. Bryan, is the sensor return wire always the middle wire on the
No.
connector?
No, I tend to assume it is, but it's not always.
That makes
And
total
that assumption is, and I'm pretty, a lot of times I'll test a sensor without even getting the schematic. I know one's got to be ground. One should have 5 volts all the time, and one should change. I can back probe 3 wires quicker than I can go look up something in ALLDATA.
Thank you.
So
Brian,
Brian,
Yes.
so I do understand. I mean, going back to what you mentioned on the pressure, outside, temperature pressure, and the pressure inside the engine. So I'm just like, because I'm brainstorming right now. I know we probably need the ambient pressure or strategy to start the car up, but once the car runs, how the system gets that? Why is useful that temperature? That's that temperature for the system.
Well, because remember I said we measure our fuel by weight. And I'm getting a little ahead because I'm going to really get into this in our fuel discussion. But we measure our fuel by weight. If I change the temperature of something, does its weight change?
Yes.
No, it doesn't.
Yeah, absolutely. That's why we need to know the temperature, Alberta, because as I change temperature, I change weight. So if I'm going to correctly put the precise amount of fuel in that I want, I need to know the weight of the air. So we use these different sensors on the engine to really, when you break it down, measure the weight of the air coming in, measure the speed that the engine is rotating. Once we know those two things, now I know precisely how much fuel I need to put in so I am the most efficient.
But
And
I actually thought about that, like the injection pulse. But my question is, see, that's the thing, I answered that, but then something in my mind is like, what about this? So,
No.
yeah, I mean, but like on all older cars, right now in new cars, you can measure the amount of pressure that you can get from the fuel pump. But in old cars, you just put 12 volts straight to the pump, and that thing is just going to be running at a certain amount of pressure. How can that, like in that case, the way you mentioned about the way, how can that differentiate, like on that?
Okay. So two things. First of all, the standards that we built cars to in 2000 are different than the standards we build cars to today when it comes to emissions. The other is that's why we have an oxygen sensor in the exhaust system to make those fine adjustments to compensate for that last little bit of difference in pressure that we might not be measuring. Also, traditionally systems were low pressure fuel, and by low pressure, even high pressure port injection, 60 psi. Whether I'm at 60 psi or I'm at 62 or 58, I can compensate for that. On direct injection systems, I might be at 4,000 psi. The difference between 3,000 and 4,000 is a lot. So that's where they're really focusing that a lot more now. Also, is we controlled things best we could going back to 1980, and that was cutting edge technology then. It made our heads hurt trying to learn it. But yet there's a lot of things it didn't do, and those things have evolved and changed as our desire for cleaner and cleaner air and stricter emission standards have gone into effect.
Okay, so pretty much that strategy is only just for fuel related strategy, right? Because the air is pretty much the same. That one, I mean, the amount of travel that the piston does is the same. Either if we're at
Right.
in Colorado, it's going to be the same thing. Okay.
Yeah, so its fuel related strategy could also affect the transmission strategy.
Sir Brian, what
Yes.
are the two load sensors?
The two load sensors are the MAP sensor, manifold absolute pressure, and the MAF, M-A-F, and that stands for mass airflow.
Okay, thank you.
And we will be getting into mass airflow, I thought today, but it's going to be tomorrow, I believe.
Sorry, I don't mean to hold us up anymore. I know we're, but and I
No,
know
no,
you're
if
probably
you guys are learning, you're not holding me up. I'd rather not get to a module in this class and have everyone learn than everyone quiet bored to death just because we got to get to all the modules.
So I get that colder air is denser, and it has more oxygen in it. But when we say we can compensate, is that directly due to the stoichiometry of it? So we're trying to keep it at 14.7 to 1.
Roughly, yes. We don't actually operate engines at 14.7 to 1, and I'll get into that in the fuel section. But yes, we do want to manage that ideal stoichiometric mixture, and we may be slightly off of stoichiometric deliberately. And I'm talking 0.002% off. I mean, we're talking, but that's actually how we measure. We're measuring very, very precise. So that ideal mixture, and we are using all that to try to compensate and get to that ideal mixture, because that ideal mixture is weight. It's 14.7 pounds of air for every pound of fuel. It's not parts. It's not, pieces. It is weight. So it's all about weight. So we know what the weight of the fuel is, and we're getting better and better at measuring that, because on newer cars, we have more fuel pressure sensors. So we know the computer knows the precise weight of the fuel. We know the fuel's temperature. Many of these cars have a fuel temperature sensor. We know the pressure of the fuel, and we know the size of the orifice of the injector. And if I open it for 1 millisecond, I know exactly the weight of fuel that is going to flow through that injector at that pressure in 1 millisecond. We can measure fuel like nobody's business. Air is the big mystery. How much does the air weigh? And that's going to change with altitude. It's going to change with temperature. And then also I need to compensate for how much air do I have? What's the air volume?
Got it. So what, tying in all those sensors, which sensors would you say have the most influence or relation to trying to, so it would be all of those, right? Like the map sensor, the bar sensor.
That is an awesome question, Christopher. And I'm going to defer that a little bit till we get into our fields, because I actually have a couple charts that show that, and that's called sensor priority. So that is an awesome question. And sensor priority is different on older cars, especially pre-OBD2, but really pre-2000 compared to post-2000 cars. So when we get into fuel control, I break down sensor priority, and I'll show you how that works.
Got it. Thank you.
And I have a couple of charts and slides I made just for that, because that is an awesome question, and that's why I address it. The problem is you're a couple weeks ahead of me. So Hall effect sensors are frequently used where accuracy and fast response are important. They contain a powerful magnet. As the magnet passes over a dense portion of the trigger wheel, 5 volts is pulled to ground, about 0.3 volts through a transistor in the sensor. When the magnet passes over a notch in the trigger wheel, the 5 volts is restored. Hall sensors can be used for crank sensors, cam sensors, vehicle speed sensors, ABS, brake position sensors. Remember, a Hall doesn't have to be on something that rotates. A Hall switch works if I'm going this fast or going that fast. So speed has no effect on the Hall's ability to be accurate and work. So clutch pedal position, power window, sunroof, just to name a few. So we talked about memory, right? My window knows top and knows bottom. Some of them use a Hall switch, and it actually counts how many notches up, how many notches down. Brake pedal position sensor. We no longer want to know, is the brake on or off to turn the lights on? We want to know, how far are you pushing the brake down, and how fast did you push it down? Right? Are you slowly applying the brakes even though you're pushing down further and further, or did you suddenly push it down? That's going to have what? A different strategy for our braking system, for our ABS system, potentially even for what our transmission and engine are going to do. So we're using Hall switches or sensors more and more places.
Mr. Brian,
Yes.
Sorry, I must have missed this. Did you start talking about the hull yesterday? What exactly is the hull in this context?
Ah, the hull is a switch, and I got some pictures coming up to explain it for you, Dell.
Okay. All
Because I
right.
just started talking about Hall. It's Dr. Hall, if I remember correctly, invented this thing. So that's why we call it a Hall switch. So Hall sensors do a much, or switches, because they really truly are a switch, do a much better job at detecting movement at low speed when compared to permanent magnet sensors. So here's a wiring diagram. And if you look, I have a crank position sensor and a cam position sensor. So a Hall switches, although many of them use 5 volts, they can use 12 volts, they can use system voltage, they can use anything. But if we look, we have our ignition feed, which in this case is power. I have reference low, which we know from our electrical discussion is another name for ground. And then I have the cam sensor signal input. Over here, I have ignition feed, reference low, and crank sensor input. So what do I have? I have a power, a ground, a signal return. A power, a ground, a signal return, just like every other 3-wire sensor. Okay, so electrically, shouldn't this drop all of my applied voltage? Absolutely. Should I get a varying signal on my signal return? Yes. So the question is, what should the signal look like? So here in this example, I have a Hall switch or sensor. When there's no blade, we have 5 volts. When the blade comes through, it blocks the magnetic field and goes to 0 volts. So what I get is a square wave or a digital signal. I can see my friend, I can't see my friend. I can see my friend, I can't see my friend. I can see my friend, I can't see my friend. I can't see my friend. Oh, I see my friend again. Oh, I'm sorry. Yeah, I see my friend again. So simple open and close. And so you can see here, we can do some neat things with a Hall. Although it's only on or off, it's digital, I can change how long I want it to be on for. So now I can have a different amount of on for each cylinder. I could have different amounts of on my brake pedal between big gaps or small gaps, which will tell it not only is it moving, how fast it's moving, but very quickly with a small amount of movement, where it is. So by varying the notches, we can tell where we're at very quickly. This is one of the things that's allowed cars to start so much faster. New cars you don't even hear the engine turn around once before they start. Part of that is because they use Hall switches. And because they code the pickup for the Hall switch, it knows exactly where in that 360 degrees it's starting to crank from. So it knows exactly which cylinder to give fuel and spark to start that engine up without having to go around once or twice to figure out where everything is. That lowers emissions. So these are extremely fast switches. Again, 3 wires. I'm going to test them like any 3-wire sensor. If I'm going to look for my output, if I move it real slow, I could use a DMM and watch the voltage go from 0 to 5 or 12 or whatever it's using. Or I could use a scope and actually have it go faster. So here you can see I have 2 Hall switches, one for my crankshaft sensor and one for my camshaft sensor. And on this, my crankshaft sensor goes around once, twice, and the crankshaft cam went around once. Also, I can see on this car, this is supposed to be exactly in the center of this. So I can bring cursors up or draw lines and see that, yep, it's exactly in the center. That means my camshaft and crankshaft, that we'll be learning more about when we get into engines, are exactly aligned to each other. They're exactly where they should be. If this was not lined up to the center of this, that would mean that maybe a chain stretched or a timing belt jumped a tooth or a timing chain jumped a tooth or something like that. So we can use these sensors for a lot of testing and measurements. So we've used these sensors not only to test them in case a sensor goes bad, but also we use them to test other things because they're so accurate.
Okay,
so-
this might be a dumb question and I'm just not following it right now, but okay, if you can go back to the other diagram, please.
Yes.
Okay, why is there not, no, not that one, though, yes. Why is there not one, I guess, not a loop, but a little thing on between the,
Right
yes,
here?
why isn't there anything, yes.
Okay.
Because symmetry wise, you know, you're saying
Right.
it should line, so why isn't there anything there?
Great question. And you're looking at it exactly correctly. You're looking at it going, this should be symmetrical, it should line up, it should be even, and there's something that looks like it's not symmetrical. So your analysis is perfect. So now we get to the why. Well, the why in this case is that the yellow is my crankshaft sensor and my white is my camshaft sensor. So my camshaft sensor opens and closes the valves, which allow my engine to breathe. And chapter 12, which is the next chapter we do, is going to get into all this. And then the crank sensor goes around and it makes the piston go up and down. Well, my crankshaft has to go around twice for every once this goes around. So if this goes around once, this has only gone half a turn. It goes around again, now it comes back. So that's why you see 1, 2 crankshaft revolutions, 1 camshaft revolution. So your analysis was perfect because you asked a great question. And we learned by finding the answer. And the answer is because of the relationship of the shafts.
Is that what they call the two-stroke or whatever?
4-stroke, yep. 4-stroke engine.
4-stroke?
4-stroke, because every time the piston goes up or down is called a stroke. So when the crankshaft goes around, it makes the piston go up and down and then up and down. So it does that twice in one cycle, and the camshaft only goes around once per cycle. So it's 2 crankshaft revolutions, 4 strokes, 1 cycle.
Oh.
Now I notice on this thing right here. Sorry. Oh no,
Okay,
I
go
was
ahead.
gonna say I noticed on this that it says it's a 4-cylinder. So if it was an 8-cylinder, would that space be occupied by a valve opening and closing because there's more cylinders to compensate for?
No, I think what you see would be more notches here because I got 1, 2, 3, 4. 1, 2, 3, 4. So if I had 8, I might have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I would see more notches down below on the crank because we have more hits. So they may divide that out more. And again, they may not. They could leave it just like this. It really gets down to engineers. This is an older capture. A lot of newer ones have a lot more activity on both the crank and the cam because this one's pretty crude. My crankshaft turned around between here and here. It went 360 degrees. So right here is 180 degrees. So I'm only getting a signal every 90 degrees. That's not the accuracy I want in 2021. It's great accuracy in 2000. So in 2021, I might have 60 teeth there. I might have on the camshaft, might have 20 teeth. I mean, so we've added a lot more. The relationship or ratio won't change, but we've added a lot more signal input to both the crank and the cam on newer vehicles. Why? Because we want that thing to know exactly where it's at within a few degrees of crankshaft rotation. We want to be able to start that engine.
So would this sensor be used? I don't know. I read something in the book, I believe, where they the newer cars or the electric cars, they stop it on purpose at the same time every time. So like you said, that it can fire up, it knows where it's at on its firing.
Right. So it's not necessarily stopping at the same spot every time. What they do is with the sensors, they know where it stopped. And engines tend to stop, depending on how many cylinders, one of only several places. So they don't stop all 360 degrees because of the balance of the pistons and compression and all the stuff that goes on. There's certain sweet spots where that engine is going to want to stop. And so they do monitor that. So they know exactly where it was when it stopped running because we haven't turned the key off. So we've used these sensors. We know exactly where we're at. We know who's next before we even start moving.
Mr. Brian, can you just check my thought process here? because Hall effect sensors seem like they're the opposite of a permanent magnet sensor, and that Hall effect seems to measure the interruption of a provided signal, and the permanent magnet sensor seems to induce the signal. Am I off?
That's my understanding. That's the stuff I have now. I have seen stuff written that's written exactly opposite. So, you know, I've seen stuff written both ways. But they do definitely, like I said, the documentation I have shows it work that way. But again, it's a C, not C, but it is kind of an opposite signal. But again, that's because of where the magnets are and what we're seeing. But it's also another thing is, remember, the permanent magnet makes its own voltage, where the Hall effect has to be supplied voltage, and we're just interrupting a signal by disturbing the field between the two.
Right, that's exactly what I meant to say on being opposite, where the permanent magnet is getting a signal induced into it by something turning next to it, whereas the Hall effect has a signal already, and that signal is being interrupted by something turning next to it.
Absolutely. Or slid through it, as we see here in the capture I had.
Well, interrupting the field.
Interrupting the field, yep. And so here is a camshaft position sensor. This happens to be Ford. They got rid of the distributor and they put a cam sensor there instead. And you see what? We have 3 wires. So yeah, that's exactly what they're doing, Rob. It's basically opposite, but both are relying on that trigger wheel to what? Generate a signal.
Thank you.
You bet. So Hall sensors generate what type of electrical signal?
Number 4.
Number 4, I didn't trick you?
Number 4.
It's a trick. I think it's a trick that when there's a both or none of the above, you choose that answer.
Yeah, sometimes. But in this case, I wanted to make sure everyone knows that a digital signal is a square wave. Because we use those terms interchangeably in the auto industry. We'll call it a digital signal, or we'll call it a square wave. We'll say, hey, it makes a square wave. We use those terms interchangeably, like 12 and a dozen. So I put this question here deliberately again, because we've asked something similar to this, to make sure, again, remind you, digital, square wave, they're the same thing.
To know.
So here's a speed sensor comparison. And here you can see our variable reluctance sensor or permanent magnet sensor makes an AC analog signal. It's going to change its amplitude and frequency by how fast the rotating component moves. My Hall effect sensor will change its frequency by the speed of the rotating component, but never its amplitude. It always switches from the same amount. In this example, between 0 and 5 volts. But the other example I showed you between 0 and system voltage. So we can use either one, just depends on how the engineers do it. So we did make it through our Hall effect today. So that's all of our speed and position sensors. And I turned on that lab. I wanted to make sure I got that. Tomorrow, we're going to talk about the mass airflow sensor. And I'm also going to explain to you why mass airflow sensors normally go bad and how they work and what they're doing. So people normally really enjoy that, because usually people that have had to buy a mass airflow sensor at one time or another. And so it is interesting to see how the magic works.
Interesting topics.
Okay, so Mr. Brian, there's a lot of sensors in the car, right? So if I'm comparing a car to a body, does the sensor equate to sort of like the nerves in our system?
It could, yeah, because nerves sense, absolutely.
Okay.
But at the same token, your nerves, or most of your nerves, kind of work the same way. So you don't learn about a hand nerve in a vacuum when you talk about a foot nerve or a nerve in the back. You learn how it's routed, how it works, how it does, but the actual function is very similar.
And that everything is, the nerves are sending signals to the brain, kind of like the sensors are sending signals to electronic control module or something?
You got it.
Okay.
You got it. And you can see how much our 3-wire sensors have in common. So far, everyone we've looked at has had what? A power, a ground, a signal return.
Mhm.
You know, so think about it. Think about all the sensors we have on the car. We've looked at our 2-wire sensors. We found there's not that many different. There's a switch, and there's one that changes resistance through variable resistance, whether it's potentiometer or rheostat. So we have variable resistance and a switch, 2-wire. We're on 3-wire. We've gone through a couple of different 3-wires, lots of fancy names, but I test all of them so far the same way. I check for power, ground, signal return, and compare the signal return to what I should have. So that's what I was saying. There's not that many ways we have on the car of building sensors. And even though the sensors may be built differently, electrically, there's even fewer ways we have of building these sensors and building these circuits. So as we learn this commonality, this is what allows me to look at a car I've never seen before and look at what's getting 3 wires, what has 2 wires, looking at the position, do I think it's an actuator or a sensor, and so on, and start developing a pretty quick hypothesis of what I'm looking at, even though I've never opened a manual or never seen that car before. Because I know what questions to ask and I know how to balance it against what I've learned. And that's what's allowed me to learn new cars for almost 40 years. Because when I went to school, everything was 50s and 60s cars, a few 70s. And now we don't see these cars. So I had to learn everything new. And some of it was going to school. Some of it was taking what I learned in school or taking things that I'm sharing with you and being able to apply them to new systems.
That's good to know then. So it's kind of like grouping the sensors into certain groups that have similar characteristics and knowing how they function and all.
You got it.
Okay.
And that's the method to my madness. So hopefully by the time we get to my sensors and actuators and you watch my 2 videos and do the labs, you guys are going to feel a lot more comfortable and realize you guys have learned a lot.
So it's not really, you have to know.
Fix the housing usually. What would melt it? The housings on a headlight. What can melt it?
Wrong wattage bulb. What were you saying, Del?
Oh, I forgot what I was gonna say. No, I think it's just like not. Oh, forget it. I forgot completely. My memory is short.
It was something about learning and knowing or needing.
Oh yeah, it's not knowing every single one of them in detail, but knowing the general concept then. Because how can one remember everything? Like, I don't know.
You got
be
it.
Master.
You got it. And that's how I teach. And that's why I try to break things down. I try to give us a real good foundation. We know what an electrical circuit works like. Now, when we look at these things, it's just another electrical circuit. What does it do? Conceptually, that's why I do the networking first. Conceptually, we understand a car that wants to apply its brakes or a car that wants to steer us back into the lane. We can understand the conceptual of that. Now we're talking about sensors. So, well, if I want to measure the steering wheel, for example, and it rotates, that's probably a Hall because I'm going to want to measure it going around and around very accurately, no matter how fast it goes. So if I was building it, I'd probably use a Hall switch. So if I look and I see 3 wires there, I'm probably right.
Okay, that's good to know.
I told you guys beginning of class, my job is to teach you how to ask good questions.
Are we learning?
I think so. Yeah. By the questions I'm getting, I certainly say so.
Yeah.
Yes, we're learning. We're learning from you, Tita Del.
Oh yeah.
Yes, you're awesome, Tita Del.
Oh goodness, no, thank you though.
You're welcome.
I'm a newbie, know nothing before, so I'm learning little by little, and hopefully I retain some of them. At my age, it's not easy.
Yeah, you're one of my idols, Tita Del.
Oh gosh, you're flattering me. I don't need that this morning. Sorry.
Yes, you are.
I think that you learn more than you realize. And what's interesting about automotive or interesting about these sensors or switches, we can apply it when we open our refrigerator door and the light doesn't come on. Wait a minute. That has to be a series circuit. It has to have a switch. The light bulb's the load. I can figure this out, right? I mean, I can already visualize how it has to work. So I
Sir
think
Brian,
that
are
that's
all speed
empowering.
sensor the same?
What's that?
Are all speed sensor the same? Are they all the same?
Yeah, there's only two ways we do it. Variable
Oh.
reluctance and Hall effect. Now you're going to see a couple sensors that are a modified Hall. They have a new name for them. They're able to run them on 2 wires because they ground through the sensor. But they're on the video I did. But the video shows all 4 sensors, and actually it's only 3 sensors, just 2 different ways of getting the signal off the bearing that we use on every car worldwide, period, made ever. So all 1,700 models, I showed you this how the speed sensors work.
Oh, okay. Thank you.
And
You know,
basically,
so
like you said,
that's-
you're giving us the fundamentals of how things work, because it falls back on, okay, we're not in the era where we're rebuilding things. We're just trying to discern what's faulty and what's not, and then we go in and replace. As you said, we don't need to know exactly in detail how the exhaust gas recirculation valve operates. We just know electrically, fundamentally, how it's supposed to work. That way we can test it and that are good, and then just replace the part.
Yeah, exactly. And we, like with EGR, we'll get a little deeper because that's an emission where I want to know what it does, but it's the same concept. If I command it to move and the sensor says it's not moving, and I can prove the sensor's good, or I can see the valve's not moving, it tells me I need to go there. I mean, I don't need to take, I'm not going to take their stuff apart. And that's it. I want to be able to isolate what's bad so I can make a good decision. We're not going to open it up and take a look-see inside.
Yeah, because like you said, 9 times out of 10, it's more economic just to replace the part than to spend the labor and the time removing the part, rebuilding the part. Then the customer doesn't have their car for the amount of time, and then so forth. So it's better just to replace whatever's.
Absolutely. And you can't get the parts, or even when you put it back together, it still doesn't work reliably. And let's face it, we all want our car to be reliable. So, that was one of the hardest things for me to learn, was that difference between we take it apart and find out exactly what little piece inside's bad, and realizing that, no, we realize it's bad, you put a new one on. And that's been something that happened during the time I've been in the industry, was that change of mindset. And that was, and I learned it the hard way, because I'd take stuff apart, find out what's wrong. I need this little piece. And we call up, find out, oh, they sell it as the whole thing. I go, you mean I could have stopped working 45 minutes ago and just said you needed this? So it has that's a great point. It's been a hard lesson to learn sometimes.
That's how it is nowadays, Mr. Brian.
I know
Replace the whole part.
Hey, trying to keep up, guys. All righty. Well, hey, everybody, been a great class. I look forward to seeing everybody in the morning.
Thank you, Mr. Brian.
Thank you so much,
See you
Mr.
tomorrow.
Brian.
Thank you, Mr. Brian.
Everyone.
And bye-bye. Bye, everyone.
Bye, everyone.
Brian. Everyone.
Sayonara.
God bless everyone.
Bye,
Thank
Mr. Brian.
you.
Bye, classmates. Thank you.
You're
Bye-bye.
welcome. Bye-bye.
Bye.
Sayonara.
Bye, classmates. See you tomorrow.
Bye.
Bye.
Thank you.
Domo arigato.
See